This is a tutorial to review the electromagnetic spectrum, spectroscopy, and the Bohr's model. The electromagnetic spectrum is the collection of all the possible electromagnetic waves that we have in the universe. And when we talk about electromagnetic radiation or waves, maybe we don't really know what we're talking about until we actually recognize those types of waves. So for example, when you're listening to the radio, those are radio waves. When you're heating up something on the microwave, those are these type of waves, microwaves. Gamma rays are part of the electromagnetic radiation, and they're very high energy waves. The only part of the electromagnetic spectrum, this collection of all the electromagnetic waves, that we can actually see, and that is the visible light. That is why it's visible, because we can see it. So all the colors you see here are part of what we call light. When we're talking about light, we have to give a definition to it. So it has been proved that light behaves like a wave, which is an oscillation that goes up and down, up and down, up and down to the same position, or it also behaves like a particle. Okay, so it has like this double personality, I would say, behavior, like a particle or like a wave. So that wave, it's part of the electromagnetic spectrum. It's part of the spectrum that I just showed you. It's over here. Light is in this section of the electromagnetic spectrum. It's called visible light. If we want to measure the energy of that light, because every wave in the electromagnetic spectrum has a specific energy, that will be measured as the energy of a light photon, which is a discrete packet of light. It's like a small minimum amount of light that we can measure. It's called a photon, a discrete packet of light energy. This seems to be very abstract, but we're going to try to focus little by little on each of the things that I just said so that you can understand everything way better. Okay, so let's focus first on describing what a wave is. What is a wave? Waves are energy carriers. We cannot see them, but they are out there, and they go through different kind of mediums, through water, through air, sometimes just with no medium, through the vacuum. Those waves are oscillations. See, up and down, up and down. There are like very important characteristics of the waves that we need to know how to measure. One of those is the wavelength, which is the length of a wave. If we want to describe what the wavelength is, we want to say that it is the distance between the crest and the crest of a wave. So it would be the distance between wave crests, between one point of one wave to the same exact point of the next wave. Okay, that is the wavelength. As we have seen before, when we're measuring length, we need to use units that are the appropriate ones for length. In this case, are going to be meters or nanometers. If we talk about nanometers, it's because there might be a case where the wave is very, very small. So to measure that wave in meters makes no sense. We need a smaller prefix, a smaller unit. So something that we need to remember is that 1 nanometer equals 10 to the minus 9 meters. Okay? And we're going to be working with this later on. So 1 nanometer is way smaller than a meter. All right, so this is wavelength. Something else that you need to know about the wavelength is that wavelength is represented by a symbol, which is this one over here, lambda. Okay, this symbol that you see over here is called lambda, and that's the symbol that we use for wavelength. All right, so now we know that light is part of the electromagnetic spectrum, that light behaves like a wave as well as a particle. And if we're talking about waves, now we're analyzing what they are. And the first characteristic we're learning is that wavelength is the distance between the two crests of a wave. And it's measured in length units, which is going to be either nanometers if it is very small or meters if it is a little bigger. That said, we're going to move on and we're going to go over another very important characteristics of waves. Frequency. The frequency of a wave is the number of wavelengths that passes through a given point per second. That means that if, for example, I have this point over here, the number of wavelengths that is going to pass through this point per second will be the frequency of that wave. Is how often it passes through that point, okay? So to measure frequency, we are going to be using frequency units. And frequency units are going to be hertz or 1/seconds, which is the same as seconds to the minus 1. Okay, so again, it's the number of wavelengths that passes through a given point, specific point in a second. That is the frequency, how often it passes through that point. All right, so we also need a symbol to represent the frequency, and the symbol that we're going to be using, it's going to be, let me point that out, it's going to be this symbol over here. Okay, it's kind of a V, it's not exactly like a V, but that's the symbol for frequency. All right, so now we know what is the wavelength of a wave, and we know what is the frequency of a wave. A new thing that you need to know, the speed of a wave. What is the speed of a wave? The same as the speed of a car or the speed of a person, okay? It's how fast the wave is traveling through space, okay? It's how fast you go per unit of time. So if it is how fast you go per unit of time, you will be measuring the length you go through per unit of time, which is going to be the seconds, okay? So the units that we use in order to measure the speed of the waves is meters per second. How much length you have attained or how far you have gone in a specific amount of time, meters per second. The speed of a wave, however, it's a number, it's a constant that won't change no matter what, okay? So regardless of the wavelength or the frequency of the wave, all the electromagnetic radiation travels at the same speed. And that is what is it's a very famous number. It's called the speed of light, okay? So the speed of light, as you see it here, is 3.00 times 10 to the 8th meters per second. That means that in 1 second, the light can travel 3.00 times 10 to the 8th meters, which is a very, very, very big distance. All right? Okay. The letter that we use, the symbol that we use in order to represent the wave speed is going to be C. All right? Now that we know what the wavelength is, what the frequency is, and what the speed of the wave is, we're going to relate the three of them through an equation. There is this equation that relates the speed of light, the wavelength of a specific wave, and the frequency of that wave. So we know that the wavelength of the wave times the frequency of the wave, it's going to be equal to the speed of light. What is the meaning of this? The meaning of this is that mathematically, the wavelength and the frequency are inversely proportional. That means, as this is a constant number, C is a constant number that doesn't change, that means that when, let me write this in another color, when the frequency is higher, the wavelength is lower, okay? And when the wavelength is higher, the frequency will be lower. They are inversely proportional, okay? If we want to say this in a different way, we would read what it says over here. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. So you have two pictures over here that represent pretty well what I just said. The longer the wavelength, the smaller, the lower the frequency, because we have the lowest amount of waves passing through the same point per second, okay? And the shorter the wavelength, the higher the frequency, because we have a bigger amount of waves passing, or wavelengths passing through the same point per second, okay? So again, we have this great equation that is going to help us relate the frequency and the wavelength of one wave, because one times the other, it's equal to the speed of light. Okay, and remember, the speed of light is measured in meters per second, the wavelength is measured in meters, and the frequency is measured in hertz. Here is another representation of what I just said. The speed of light doesn't change. It doesn't change. The speed of the wave is going to be the same. What will change will be the frequency and the wavelength. So, the longer the wavelength, the smaller the frequency. Okay? The shorter the wavelength, the more frequent it will, the higher the frequency of the wave. You have all the colors. Each color has one wavelength, and each color has one type of frequency. And this is what we're going to be talking about next. How to find the frequency of a light that has a specific color, how to find the energy of that light as well. So, going back to what I said before, remember, light can behave as a wave or as a particle. We say that it behaves as a particle because it behaves when we want to measure the energy of the light. We have to measure the energy of the photons, which are particles of light that are quantized, that they're specific discrete amounts of light energy. That's called a light photon, okay? So I'm going to read what the slide is saying. Light energy comes in discrete packets called photons. Light energy is quantized, which means that you can only have discrete amount of light energy. So if somebody is asking you to calculate the energy of the light, you will be calculating the energy of these particles of light, these discrete packets of light called photons. How do you calculate the energy of a photon? Well, the energy of the photon is going to be equal to a constant called Planck's constant, and it's this number that you see over here, 6.626 times 10 to the minus 34 joules times second. That would be Planck's constant, okay, this over here. And we will multiply this to the frequency of the light. And as you knew from previous slides and from the other tutorial, the frequency of light is the number of wavelengths that goes through the same point per second, okay? So if I want to calculate the energy of a photon and I don't have the frequency, there's a way I can calculate that frequency. The frequency can be calculated using the equation that we have learned before, that says that light has a speed that equals its frequency times its wavelength. Remember, its frequency times its wavelength. If I want to know the frequency of the light, and I know the wavelength, and I know the speed of the light, I will be able to solve this equation. And this equation that you have over here, it's very similar to it's exactly an algebra 1 equation, and I'm going to show you how. If you have an equation where you have 4 equals 2 times x, and you want to solve for x, the only thing you have to do, and I know you know this very well, is to divide both sides by 2 so that you can solve for x, right? So it's going to be 2 over 2 is 1, and 4 over 2 is 2, so x equals 2. Well, if I have an equation like this one, if I have my formula like this one, and I want to solve for the frequency, I have to do something that is very, very similar. I will just have to divide both sides by the wavelength, and I will get the frequency. I will be able to solve for the frequency. So from here to here, if I want to calculate the frequency by solving this equation, I will know that the frequency equals, remember this one and this one cancel out, equals the speed of light over the wavelength. If I plug this in here on this equation on the top, energy of the photon equals Planck's constant times the frequency, I will end up having this equation over here on the bottom. The energy of the photon is Planck's constant, which is what we had here, Planck's constant, times the frequency, which is the speed of light, over the wavelength, which is the speed of light over the wavelength. And that's a way to calculate the energy of light, by calculating the energy of a photon, which again is a particle of light that is quantized. It has a specific and discrete amount of energy. All right, now let's see an example that we saw the other day, and I'm going to go over that example again. I'm going to make this bigger. Well, here we have an example, which is the example that I gave you in class the other day. I'm going to go over that example again because it represents really well what we have learned before. Remember, light behaves like a wave that has specific wavelength and specific frequency. And if we talk about visible light, the visible light is going to be the combination of all the colors in the visible spectrum, and each of the colors is going to have one wavelength and one frequency and a certain amount of energy. In this case, the problem is telling us that we have red light, okay, red light that has a wavelength of 660 nanometers. So the wavelength is 660 nanometers, and we want to calculate the frequency, okay? We want to calculate the frequency. We know the wavelength, we want to calculate the frequency, and we have red light, which is this part of the visible spectrum of the visible light, which at the same time is in this section of the electromagnetic spectrum. Okay, so if we want to do that calculation, the first thing that we need to remember is that the speed of light equals the frequency of the wave times, the wavelength of the wave times the frequency of the wave. This is the speed of light times the wavelength equals the wavelength, times the frequency. We know the wavelength. We know the speed of light. Can we solve for the frequency? Yes, we can. As we would do in an Algebra 1 problem to solve, what we're going to do is we're going to divide both sides by the wavelength, and we're going to solve for the frequency. So we know that the frequency is going to be equal to the speed of light over the wavelength. Okay? This is the equation we're going to be using in this problem, where we're relating the speed of light with the wavelength with the frequency. And again, we're solving for the frequency as if it was an Algebra 1 problem, where you're just dividing both sides by lambda. Now, let's plug in the information we have here. We know that the speed of light is 3.00 times 10 to the 8 meters per second. And we know that the wavelength is 660 nanometers. We have a little problem here. That problem is that the nanometers and the meters cannot be divided one by another. You need to have the same units in order to operate, in order to divide. So what you want to do first, the first thing that you're going to do before you operate here, before you plug in the numbers in the calculator, is you're going to convert the 660 nanometers into meters. So 660 nanometers will be converted into meters. And how are we going to do this? Well, because we need to remember, and if we don't, it's okay, now we know it, that 1 nanometer equals 10 to the minus 9 meters. Okay? So if we have 660 nanometers, we do it over 1, we multiply this by a fraction, and we're going to use this equality over here in order to convert the nanometers into meters, because we know that 1 nanometer is 10 to the minus 9 meters. So nanometers and meters, I cancel them, and I multiply 660 times 10 to the minus 9, okay? And the answer will be 6.60 times 10 to the minus 7 meters. And now you will be asking, why, Miss Cody, but what is 10 to the minus 7? Well, because I have multiplied this number over here times this number, and then I have transformed the number into scientific notation, where you can only have one number in front of the decimal point. Okay, so we have moved the decimal 2 positions to the left. That's why we have here to the minus 7 and not to the minus 9. All right, so this is our wavelength in meters. What we're going to do is we're going to go back to this equation over here, and we're going to solve the equation. So the frequency equals 3 times 10 to the 8 meters per second divided by 6.60 times 10 to the minus 7 meters. Okay, so as you can see, you have meters here and you have meters here. You're fine, you can divide. And the answer will be 4.54 times 10 to the 14th, okay? To the 14th. Seconds to the minus 1, or, which is the same, hertz. Both units are okay for the frequency, hertz or seconds to the minus 1. Okay, so we know the frequency. This is the frequency, 4.55 times 10 to the 14 seconds to the minus 1, or hertz. We already calculated the frequency. So we have the frequency here, which is frequency equals 4.54 times 10 to the 14th, okay? Hertz, or seconds to the minus 1, which is the same, or seconds to the minus 1. Okay, so now that we know the frequency, the next question is, what is the energy of the photon? All right, so I'm gonna erase this. Now we're gonna calculate the energy of the photon. Something that you need to remember then is the equation for energy of the photon, which is the energy of that red light. The energy of a photon, okay, of a photon is going to be equal to Planck's constant, which is a constant number, times the frequency of that light, okay? So how do we do this? Well, if the energy is equal to Planck's constant over times the frequency, we just need to plug here, instead of the frequency, we're going to use the number that we calculated before, which was 4.54 times 10 to the 14th seconds to the minus 1, okay? That was our frequency. Planck's constant, it's a constant. It's always the same number, and it's 6.626 times 10 to the 34 joules times second. So what do? We plug these two numbers in this equation and we solve the equation. This is the energy of a photon of red light. So it's going to be 6.626 times 10 to the minus 34 joules times second multiplied by 4.54 times 10 to the 14th seconds to the minus 1. Okay, and this will equal to 3.118 times 10 to the minus 19, and the unit that we use for energy is joules. Okay, and that is the answer to our problem. So when light goes through a prism, it happens what we see when we analyze the rainbow. We see something called the visible light spectrum. Okay, this spectrum is a continuous spectrum because it has no gaps in the middle. There's no gaps here in the middle. There's no gaps at all. So that's why we call it a continuous spectrum. Okay, a continuous spectrum. So the continuous spectrum of light shows all the wavelengths and all the frequencies of the colors that are the components of white light. So for example, red light has a wavelength of 700 nanometers, okay, and the violet light has 400 nanometers. So the closer you are to the red part of the visible continuous spectrum, you will have higher wavelengths, you will have longer wavelengths. Okay, longer wavelengths, as you can see over here. The more you go to the violet part, you will have shorter wavelengths, as you can prove over here. So remember, wavelength and energy, it's inversely proportional because the energy is directly proportional to the frequency. So when we have longer wavelengths, we will have lower frequencies. Okay, and the shorter the wavelength it is, the highest the frequency. And frequency and energy are directly proportional. That's why when we have low frequency, we have low energy, and when we have high frequency, we have high energy. So again, light separates into this continuous array of colors, and the white light would be the mixture of all these different colors. The continuous spectrum of light can be seen in the electromagnetic spectrum in this little area called the visible light. Okay, in this area with wavelengths that go between 390 nanometers to 760 nanometers, more or less, or 380 nanometers to 750 nanometers. These are the colors that are the components of the white light, and those are the colors of the continuous spectrum of light. These colors, as you can see, each of them has a specific wavelength and a specific frequency. If you go to and check the bigger picture, you can see how in the electromagnetic spectrum, the gamma rays and X-rays are going to be the type of electromagnetic radiation with the highest frequencies and therefore the highest energies and the lowest wavelengths. Okay, so they will have the highest frequencies. You see, this is a very big number, and the lowest wavelengths, this is a very small number. On the other side of the electromagnetic spectrum, we will have, for example, the radio waves that have way lower frequencies, as you can tell over here, but they have way higher wavelengths, okay, because 10 to the second is way bigger than 10 to the minus 16. So the visible light, which is in this area of the electromagnetic spectrum, again will be between more or less 390 nanometers and 760 nanometers of wavelength, okay, and their corresponding frequencies that you can have here. So 380 nanometers will correspond to 668 terahertz, and 750 nanometers will be around 484 terahertz, okay, and this would be the energy that corresponds to each of them. So again, this is the electromagnetic spectrum. On this side over here, gamma rays, X-rays, you have the highest frequencies. On the other side, you have the lowest frequencies, okay, the lowest energies. Sometimes when we have just one type of atom, for example, a helium lamp, or we have a hydrogen lamp or a neon lamp, what we see, it's not a continuous spectrum, okay? We will see something called an emission spectrum, which shows specific frequencies of light emitted by the atom or the atoms that are in our lamp. How does this work? Well, first of all, we need to understand that the emission spectrum, it's not a continuous spectrum. As you can see, it has a specific lines of colors that belong to specific wavelengths and frequencies, and these colors and these lines are unique. This combination of colors and lines are unique to each type of atom. So therefore, this is going to be the emission spectrum of hydrogen, this one is going to be the emission spectrum of mercury, and this one is going to be the emission spectrum of neon. What means that for hydrogen, the photons, the colors that we will see, the frequencies that we will see will be only this violet one over here, the blue one over here, and the green one over here, and the red one over here. How does this happen? Well, we need to go back here and let's read this together. The emission spectrum shows the specific frequencies of light emitted by an excited atom. And that is key to know that it's an excited atom. What is the meaning of this? Well, it means that we are, in this case, for example, we had a lamp that is going to be exposed to a high voltage. And because of that, the atoms of helium that are in the lamp will be very excited, and they will start emitting energy in terms of photons of energy. Okay, so let's see a simulation that might help you understand how this works. The simulation that I'm going to show you next explains how the emission spectrum is created. Okay, how for each type of element, each type of atom, we have a specific emission spectrum. I'm going to reset this and I'm going to go to just one single atom. If we have a hydrogen atom and we expose that atom to a voltage, the electron of the atom, the electron of that hydrogen atom is going to get excited and it's going to go up to a higher energy level. From that higher energy level, I'm going to go in slow motion. It will go back down to a lower energy level. Okay, if we have multiple hydrogen atoms in our hydrogen lamp, okay, or the neon lamp, if we have multiple hydrogen atoms, which would be this case, and we expose those atoms to a voltage, okay, these hydrogen atoms are going to be very excited and they're going to go from the lower ground energy levels to higher energy levels by absorbing energy, absorbing photons. What happens that when they are in these upper energy levels, they are not stable and they want to go back down to the lower energy levels. How do they do that? By emitting a photon, okay? By emission of a photon. So what they do is they will emit those photons, and each of those photons will have a specific wavelength and therefore a specific frequency. If we have our spectrometer over here, that will read the blue, in this case for the hydrogen, the violet line, the blue line, the green line, and the red line. Why those colors? Because the photons that the hydrogen electrons are emitting when they're going from the highest energy levels to the lowest energy levels have these specific wavelengths over here. So they will have these specific wavelengths over here for the red color, for the green, for the blue, and for the violet. Okay, that would be for the hydrogen. If we have another element, if we have, for example, neon, which was the other lamp that we saw the other day, as you can see, the colors that the neon atoms are going to be emitting are going to be different because the electrons, I'm going to put this in slow motion, because the electrons of the neon atoms that are being excited in higher energy levels, when they go back down to lower energy levels, they emit photons that have other frequencies and other wavelengths. So those are read as different colors. That's why when we analyze the neon in the emission spectrum of neon, we have these different colors. The red one corresponds to a frequency that it's or in a wavelength that is over here. The orange ones will be a frequency or a wavelength that is over here. And the yellow ones, the green ones, the blue ones, and the violet ones, and so on. So as you can see, I was pointing the mercury, but I meant the neon over here. So for the neon would be the same. All these colors over here are because the electrons that are being excited, the neon atom, when they go back to the ground state or back to the lower energy levels, they emit photons with frequencies and wavelengths that fall into this area of the visible light spectrum. Okay, so each color has a corresponding wavelength and each color has a corresponding frequency, and that's why each color corresponds to one part of this or one line of this spectrum, and we just see these colors because these are the only photons that the electrons of the neon are going to be emitting when they go from the higher energy levels after being excited to a lower energy level. Again, I'm going to show you this for the last time. If I reset this and I put it in slow motion, we are exposing the neon atoms to a high voltage. We're exciting the neon atoms, and exciting the neon atoms means that the electrons of the neon atoms are going from lower energy levels to higher energy levels. What happens that to be excited and to be a high level of energy is not stable. They will go back down to the lower energy levels and they will emit these photons of light. And those photons of light that have these specific frequencies that fall into this part of the visible light spectrum and therefore have those colors. The first person to explain the emission spectrum of different elements was Niels Bohr. So the question at that time was, why were these specific lines of color instead of all the colors, and why were the colors always the same from the specific element? Well, Niels Bohr, he developed a model of the atom, specifically the hydrogen atom, and he found out that the electrons, and the electron of the hydrogen atom has one electron. The electrons in general in the atom are around the nucleus, and they are in orbits or energy levels that the farther you go from the nucleus, the higher energy you will have. The closer you are to the nucleus, the lowest energy you will have. So the energy of the electrons would depend on the distance to the nucleus, okay? So the farther there is the electron, the higher energy you will have. The closer the electron it is, the lower the energy of the electron will be. So that said, he found out that when you excite an atom, as we saw in the simulation in the previous tutorial, when you excite an atom, for example, when you excite an atom of hydrogen by adding some voltage, okay, when you excite the atom, when you excite it by adding some voltage, the electron that was in a lower energy level will go or jump up, it will jump up to a higher energy level by absorbing one photon of light. Okay, so when the electron is going from a lower energy level to a higher energy level, it absorbs a photon of light. What happens? What happens here is that the electrons that are in higher energy levels, because they have absorbed a photon, are not stable, and they tend to go back to the ground state, to the lower energy levels. They tend to go back. When they go back from the higher energy levels to the lower energy levels, they emit a photon, okay? They emit a photon of light. In this case, the photon of light you see is the purple one because the frequency and the wavelength corresponds to the violet part of the continuous visible spectrum. That's why what we see here as the photon that was emitted was in this range of wavelength. What we see is the violet color. So again, in the hydrogen atom, when the electrons are excited because they are exposed, the atom is exposed to voltage, for example, they go up to higher energy levels by absorbing a photon, okay, absorption of a photon where the potential energy, the energy of the electron becomes higher, okay? And then when they are in higher energy levels, as they are not stable, they will tend to go to lower potential energy levels, so from the higher energy level to the lower energy level by emitting photons of light. By understanding Bohr's model of the atom and how the electrons, when they absorb a photon of energy, go to upper energy levels, and when they emit a photon of energy, it means that the electron has gone down to a lower energy level. We're going to differentiate two things, or two situations, two concepts in terms of energy. We are going to differentiate between the energy that the electrons have at a specific energy level and the energy that the electron needs to absorb or needs to emit to go from energy level to energy level. Okay, so as we know, that the energy of a photon, it's quantized, as we know that these are specific packets of energy. The photons have a specific amount of energy here and here. We also need to know that the electrons are also quantized. Therefore, it means that the electrons have a specific amount of energy when they are on each energy level. So this electron over here has a specific amount of energy when it's in level N3, and it will have a specific amount of energy when it's in level N2, and it will have a specific amount of energy when it is in level N1, which is called the ground state. Okay, so again, an electron, I'm going to read this out loud. An electron can only have discrete amount of potential energy. It can also have a specific amount here, a discrete amount here, and a specific amount here. Okay, within the atom, there must be distinct energy levels. So we have energy level 1, energy level 2, energy level 3. And when we talk about energy levels, we need to think about a staircase or a ladder. You can be stepping on one of each of the steps, but you cannot be in between. The energy levels is the same. Okay, you can have and you will have a certain amount of energy here and a certain amount of energy here. Okay, but there's no way you can have something in between. That's what I was trying to say when using this example. So again, there are two concepts that we need to understand here. One is the energy that is absorbed or released by the electrons when they jump from one state to another, which is the energy of the photon. Okay, and another thing is the energy that the electron itself has when it is in a specific level of energy. So this electron will have the specific energy corresponding to level 3, which is n equals 3. Okay, so again, we have to differentiate between the energy of the photon and the energy of the electron on each level of energy. When we have to represent the energy levels, we can either use the model of the atom that I just showed you, this one over here. I'm going to make it a little bigger here. This one over here, when we have level 1, level 2, level 3, level 1 is going to be N1, level 2 is going to be N2, level 3 is going to be N3. Or we can also represent this with in this form, okay, as N1, the ground state, level 1, N2 will be the second level of energy, higher energy, level 3, level 4, 5, 6, and so on. Okay, so there are two ways of showing the levels of energy of an atom. Again, the N1 is going to be called ground state. Okay, so as I was telling you, the energy of a photon will be the energy that the electron needs in order to jump from one energy level to another. Okay, it can be either going up to a higher energy level or going down to a lower energy level. That is the energy that the electron has to absorb or emit to jump from energy level to energy level. That energy of the photon, we already know this equation. It's going to be equal to Planck's constant times the frequency. Something new that you need to learn right now will be the energy that the electron itself has when it is in a specific level of energy. So, for example, an electron that is in level 1, N1, will have an energy that is equal to minus 2.18 times 10 to the minus 18 joules divided by the level square. So if it is level 1, it will be divided by 1 square, okay? If you want to know the energy that an electron has on level 2, then it will be the energy of the level 2, n equals 2, would be minus 2.18 times 10 to the minus 18 joules divided by 2 square, and so on. Okay, so in general terms, the energy of the electron in a certain amount of, in a certain level of energy will be this number divided by the level of energy squared. Okay, so again, another example. If an electron is in level number 6, okay, N6, if the electron is over here, the energy of the electron will be minus 2.18 times 10 to the minus 18 joules divided by 6 squared. Okay, that is the energy that the electron has at each of these energy levels. All right, so now we need to think about something. When the electron changes from energy level to energy level, there will be a final energy, which is the energy that the electron has at the end, at the final energy level. Okay, for example, if I have the electron coming from N1 to N2 is jumping up from N1 to N2, the final energy level will be N2, and the initial energy level will be N1. So the difference in the electron's energy from the initial energy level to the final energy level will be the energy at the final energy level minus the initial energy level. Okay? When we're increasing the N, when we're going to a higher energy level, the energy will be absorbed, okay? And that will be positive. When the energy is being released, then it will be negative, and it means that the energy levels are going from the highest to a lowest. So again, when we're going from a lowest energy level to a higher energy level, the difference in the electron's energy will be positive. When we're going from a highest energy level to a lowest energy level, the difference in the electron's energy will be negative. And that difference in energy will be what we call the energy of the photon, because at the end of the day, it's the energy that the electron needs to absorb or release in order to jump from one state to another. Okay, so the energy of the photon, which we knew before, the energy of the photon that we knew before, will be the change in the energy of the electron from state to state in absolute value. Okay, let's see an example in order to understand what we just did. Okay, so let's do some practice problems to understand how to calculate the energy of the electrons in certain energy levels and how to calculate the energy they need to absorb or release in order to, or emit, in order to jump from state to state, okay? This is the first example. It says, how much energy does an electron have in the hydrogen atom if it is in the third energy level? So you want to focus on, you want to calculate the energy that an electron has when it is in level N3, okay? So if this is level N1, which is a ground state, that would be the ground state. This is level 2, which will be in a more excited state for the electron to be, and this is level 2, and this would be level 3, okay? And 3. So the question here, the problem here, is asking us to find out the energy that an electron will have when it is in this energy level. That is what we want to know. And for that, we want to use the equation. Remember this equation over here that we learned before, which is the equation that relates the energy, which finds out the energy of the electron based on the energy level. I am going to calculate the energy of the electron when it's in level 3, right? So for level 3, what I have to do is I have to copy the number on the top, minus 2.18 times 10 to the minus 18 joules. That would be the energy divided by 3 squared, okay? And that will be the energy of the electron when it is in the third energy level. If I plug those numbers in the calculator, the answer will be that the energy when I am in level 3 is minus 2.422 times 10 to the minus 19 joules. That will be the energy of the electron when it is in energy level N3. Okay, now the next question. How much energy does the electron have if it is in the first energy level? Well, so we're going to be using the same equation that we have over here, and we're going to apply exactly the same formula over here. So if we want to calculate the energy when we are in level 1, we will have to divide 2.18 times 10 to the minus 18 joules over 1 square, okay? And the answer, of course, is going to be minus 2.18 times 10 to the minus 18 joules. And this is the energy that the electron has when it is in equals 1, which is the ground state. Okay, that would be the ground state. Okay, and the next question says, where does the electron have more energy? Well, if we want to calculate the two levels of energy, we need to take a look at the numbers over here. And I know that it's a little bit complicated, but if we really focus on this, we will realize that this number on the top, the energy at the level M3, it's a number that is less negative than the number on the bottom, okay? Because minus 19 makes that number less negative than the other one. So as this number on the top, E3, is less negative, it means that it's a higher level of energy. Okay, that's why the answer here would be that between the two, E3 will have more energy. And remember, the higher you go, the farther you go from the nucleus, the higher the energy level will be, the higher the energy of the electron will be as well. Okay, so we had to calculate the energy of a photon, that is absorbed to transition an electron in a hydrogen atom from N1, level 1, N1 ground state, okay, to N5, okay, and I previously drew these lines for you to see it more clearly. So that would be N5. Okay, so the idea, this is a weird 5, but it's a 5, okay? So the idea is that we have an electron which is in N1, and it's jumping all the way up to N5. And in order to be able to reach N5 and go up to N5, it has to absorb a photon of energy that has a certain value of energy, okay? It has to absorb this photon of energy that has a certain value. And that is what we're going to calculate first. The energy of the photon that the electron has to absorb in order to jump from N1 all the way till N5. And we're going to do exactly the same we did on the previous problem. So the first thing you want to do is you want to focus on the equation that calculates or helps you calculate the energy of the electron on a certain level of energy. So if we have in E, the energy for the level 1 will be E1, it will be minus 2.18 times 10 to the minus 18 joules divided by 1 squared, which is minus 2.18 times 10 to the minus 18 joules. The energy of the electron in N5 will be minus 2.18 times 10 to the minus 18 joules divided by 5 squared, and this equals, and I'm going to do this in my calculator, minus 2.18 exponent minus 18 divided by 25, and that is minus 2.18 exponent minus 18 divided by 25, and that is going to be minus 8.72 times 10 to the minus 20th, okay, let me do 20th joules. Alright, so now that we know the energy of the electron when it's here in N1 and the energy of the electron when it's here in N5, now we want to know how much energy this electron had to absorb in order to be able to jump all the way up to N5. And that will be the energy of the photon that is absorbed, okay? So the energy of the photon is going to be, remember, the absolute value of the difference of the energy of the electrons, which is going to be, in this case, the energy on the final state, which is 5, minus the energy on the initial state, which is 1. So the energy of the photon, again, energy of the photon, it's going to be in absolute value, minus 8.72 times 10 to the minus 20th, minus, open parenthesis, minus 2.18 times 10 to the minus 18th, close parenthesis, in absolute value. So if I plug these numbers in the calculator, minus 8.72 exponent minus 20 minus 2.18 exponent to the minus 18th, it will be 2.09 times 10 to the minus 18 joules. Let me do it again. So it will be minus 2.72 exponent minus 20th minus, open parenthesis, minus 2.18 exponent minus 18 close parenthesis. Yes, 2.09 times 10 to the minus 18 joules. And this is the energy of a photon that the electron has to absorb in order to jump up from N1 ground state to N2. Okay, that is the first part of the problem. The second part of the problem is asking for the wavelength of that photon. Okay, so it's asking for the wavelength of the photon. And remember, the wavelength of the photon is lambda. So in order to calculate the wavelength of the photon, we will have to use a couple of tools and resources we know. The first thing that we need to remember is that the wavelength relates to the frequency by using the formula that comes after. C equals wavelength times frequency, right? So right now we don't know the wavelength and we don't know the frequency, but actually we can calculate the frequency first. We can calculate the frequency first by using the information that we got before. Okay, so we know we have the energy of the photon that we previously calculated, which is equal to 2.09 times 10 to the minus 18 joules. Okay, we know that the energy of a photon equals Planck's constant times the frequency. So first of all, before we calculate the lambda, before we go for the wavelength, we're gonna calculate the frequency because we need the frequency in order to calculate the wavelength. Okay, that's what we're doing. We're calculating the frequency first in order to plug it in here and solve for the wavelength later on. So how do we calculate the frequency? Well, here we have the energy of the photon equals Planck's constant times the frequency. If we want to solve for the frequency, we will going to apply the what we do for the algebra 1 linear equations. Okay, so Planck's the energy of the photon is 2.09 times 10 to the minus 18 joules. Planck's constant is 6.626 times 10 to the minus 34 joules times seconds. And then the frequency is what we want to solve here. So what we do is we're going to divide both sides by Planck's constant, 6.626 times 10 to the minus 34, and 6.626 to the minus 34, and we're going to solve for the frequency. Okay, so this number and this number, they cross cancel each other, and we will have that the frequency equals 2.09 times 10 to the minus 18 joules divided by 6.626 times 10 to the minus 34 joules times seconds. So if we plug these two numbers in the calculator and we divide them, we will have 3.15 times 10 to the 15th seconds to the minus 1. Okay, seconds to the minus 1, or hertz, which is the units for frequency. We know now the frequency, so we know the frequency of the photon now, of this light now. Okay, so the frequency will be this one over here. So now we know that the frequency is equal to 3.15 times 10 to the 15th. Okay, so as we know the frequency because we calculated thanks to the previous equation, and we know the speed of light because it's always going to be the speed of light, 3.00 times 10 to the 8th meters per second. Now we can solve for the wavelength. Okay, now we're gonna be solving for the wavelength, and that's what I'm gonna be doing next. Okay, so knowing the frequency and knowing that the speed of light equals the frequency times the wavelength, or the frequency times the wavelength, yes, we're gonna solve for the wavelength. Okay, so let's plug in the numbers here. We have the speed of light, which is 3.00 times 10 to the 8th meters per second equals lambda, that we don't know, times the frequency, which is this 3.15 times 10 to the 15th seconds to the minus 1. Now, if we want to calculate lambda, we will have to divide both sides by this number, 3.15 times 10 to the 15th seconds to the minus 1, and 3.15 10 to the 15th seconds to the minus 1. Okay, so we cancel this out and cancel this out, and we have that lambda, the wavelength, is going to be the speed of light, 3.00 times 10 to the 8th meters per second, divided by 3.15 by the frequency, times 10 to the 15 seconds to the minus 1. The answer will be 9.52 times 10 to the minus 8 meters. And this is the wavelength of the photon. Okay, this is the wavelength of the photon. So again, if there was any confusion, what we have done first is to calculate the energy of the photon by subtracting the energy of the electron in two energy levels, level 1 and level 5 would be E5 minus E1. That would be the energy of the photon. Once we know the energy of the photon, we can calculate the frequency using this equation that relates the frequency and Planck's constant to the energy of the photon. And once we know the frequency, we can use this last equation that relates the frequency and the wavelength to the speed of light, and we have solved for the wavelength. Here we have another example that is a little bit more complex. It says calculate the energy of a photon that is released. Okay, it's released when an electron in a hydrogen atom transitions from N4 to N2. So the first thing that we want to do is we want to represent those levels of energy in the hydrogen atom. Okay, so we're going to have here level 1, we're going to have level 2, level 3, level 4. Okay, and remember that will be N1, this will be N equals 2, N3, and N4. So what we want to know, what we want to calculate here is the energy that is being released, the energy of the photon that is being released when the electron from being here in N4 jumps back down to, jumps back down to N2, okay, to N2. When the electron that used to be here in N4 goes back down to N2, it releases a photon of energy, and we want to know the energy of that photon of energy. Okay, we want to know the energy of the photon of energy of light that was released when the electron jumped from N4 all the way back to N2. That is what we want to calculate. And again, we might want to use the same equation at the beginning in order to calculate the energy of the electron in one of the energy levels and the other energy levels. So we're going to do all these calculations as we were doing before. Okay, the first thing that we want to know is the energy of the electron when it's in the different energy levels. So the energy of the electron when it is in energy level 4 will be minus 2.18 times 10 to the minus 18 joules over 4 squared. And the energy of the electron when it's in level 2 will be minus 2.18 times 10 to the minus 18 joules divided by 2 squared. Okay, so if I plug these numbers in the calculator, I will find out that the energy of the electron when it's in level 4 will be minus 2.18 exponent minus 18 divided by 16. It will be minus 1.36 times 10 to the minus 19 joules. And the energy of the electron when it's in level 2, it will be minus 2.18 exponent 18 divided by 4, which is minus 5.45 times 10 to the minus 19 joules. Okay, so now that we have the energy of the electrons in the state 4, in N4, in N2, we need to remember that the energy of the photon will be the same as the absolute value of the difference of the energies of the electrons, right? So it will be the same as the absolute value of the energy in the final state, which is going to be E2 minus the energy on the initial state, which is going to be E4, okay? So if I want to calculate this for the energy of the photon, I'm going to just plug in the numbers. So E2 equals minus 5.45 times 10 to the minus 19th joules minus 1.36 times 10 to the minus 19th joules. Okay, so it's the subtraction of a negative number. So if I plug this in my calculator, minus 5.45 exponent minus 19 minus, open parenthesis, minus 1.36 exponent minus 19, close parenthesis, the number, it's going to be minus 4.09 times 10 to the minus 19, but as I have an absolute value is going to be positive, so it's going to be 4.09 times 10 to the minus 19th joules. And this is going to be the energy of the photon of light that is being emitted, okay, when I am jumping. Is the photon of light that is being emitted when I'm jumping from state 4, energy level 4, to energy level 2, okay? That's what it is. Now, the second question, what is the frequency of that photon? Well, we know that there is an equation that relates the frequency with the energy of a photon, right? So that equation, remember, is the following. It's the energy of a photon, I'm going to write here pH, okay, is going to be equal to Planck's constant times the frequency. Now, do we know the energy of the photon? Yes, we do, because we have calculated the energy of the photon on the previous part. Okay, so you just need to plug in the numbers and then solve for V. I'm going to show you here how to do that, okay? So remember, the energy, I'm going to write it here, the energy of the photon that we just calculated was 4.09 times 10 to the minus 19th joules. All right, so that's it. I'm gonna go back here and I'm going to erase this, and I'm gonna start from there. So remember, the energy of the photon that we just calculated, was 4.09 times 10 to the minus 19 joules. But we also know that the energy of a photon can be calculated with Planck's constant and the frequency. So we're going to plug in these numbers over here, and then we're going to solve for the frequency. 4.09 times 10 to the minus 19 joules equals 6.626 times 10 to the minus 34 joules times seconds times the frequency, okay? And remember, this number over here is Planck's constant, and it is a constant number. And this number over here is the energy of the photon that we just calculated on the previous part of the problem. So we need to solve for this. We need to solve for the V. And for that, what we're going to do is we're going to solve this as a linear equation problem, as an algebra 1 problem, where we're going to divide both sides. We're going to divide both sides by Planck's constant. Okay, so we're going to divide 6.626 times 10 to the minus 34, and then 6.626 times 10 to the minus 34. Okay, and that way this number is 1, and the frequency will be equal to 4.09 times 10 to the minus 19 joules divided by 6.626 times 10 to the minus 34 joules times seconds, okay, which is the same as dividing the energy of the photon over Planck's constant, okay, and this will equal to, the frequency will equal to, let me do this in the calculator, 4.09 exponent minus 19 divided by, open parenthesis, 6.626 exponent minus 34, close parenthesis, and the answer will be 6.17 times 10 to the 14th seconds to the minus 1, or hertz, which are the units for frequency. This is the frequency of this photon. And that's the end of the problem.